Okay, Assalamualaikum warahmatullahi wabarakatuh. So we will continue with Kepler's Law. Okay, as we know that Kepler's Law already been invented by the scientist named Kepler. So Kepler say that the concept of circular orbit about the sun had to be abandoned. This is because that our orbit is not in circular shape but it is a elliptical. So why we say it is elliptical? Okay, so after this I will explain to you in Kepler's first law. Okay, as you have to know that the Kepler's law will be divided into three statements. Okay, so we will go one by one. Okay, so the first statement, or we can say that the first Kepler's law, okay, say that planet will be rotate in elliptical orbit. Okay, why it say it is in elliptical orbit? Because the gravitational force itself, because F, okay, F is actually proportional to 1 over r squared. Then if we have r squared, means that our orbit is not in circular but it is in elliptical orbit. That is number one. Okay, and then number two, this is our elliptical orbit. So basically we will have a semi major here. Okay, so this is our axis. Okay, this is our x-axis. Okay, then up to here we will have a semi major. Okay, and this one we will call it a semi minor. Okay, so for our semi major, we will have a two focus here. This is focus number 1 and this is focus number 2. Okay, so for focus number 1, okay, it will be occupied by the sun, and for the focus number 2, okay, will be there is no object in the focus number 2, but we have to know that there is focus number 2. Okay, so for example the planet is here. Okay, so the distance from the planet to the sun will be denoted as Q, and the distance from the planet to the second focus will be denoted as P. Okay, the Kepler first law say that the sum of the PQ means that P plus Q at the entire position will be same. Means that, okay, for example, if your planet is here, okay, then your P plus Q will be same with the P plus Q when your planet is at the what we call it, above, at the above of the orbit. Okay, so if your planet is here, then P plus Q will be same as your planet here. Okay, the sum of P plus Q will be same at the entire position. Okay, if your planet also here, then the P here plus Q here will be same with the P plus Q at this position. Alright. Okay, next we will have a second Kepler's law. Okay, second Kepler's law is basically more related to the conservation of angular momentum. Okay, because when we calculate the area here, okay, will be same as the area at this position. Okay, so okay, the planet will go from A to B. Alright, so as you can see here, alright, the movement here will be not longer, short. Okay, the movement here will be short, or the length from A to B is short, and the length from B to D is a little bit longer. Okay, so here, okay, the area shaded will be the time interval. Okay, so what the second Kepler law say that when the planet move from A to B, okay, the time taken of the planet from A to B will be equated to the time taken for the planet move from D to C. Okay, I will repeat again. Kepler's second law say that the time interval from for the planet to move from A to B is equal to the movement, the time taken of the movement for the planet from D to C. Okay, why? Okay, because the distance here is a little bit short, then the planet will move a little bit slower. Okay, why the planet move slower here? Okay, even though the distance is short. Okay, because the attractive force, okay, from the planet to the sun here is a little bit lower. Okay, and the attraction force here from the planet to the sun here is larger. So that's why at this moment, okay, the planet will move faster than this one. That's why the time taken from here to here will be same. The time taken from A to B will be same as the time taken of the planet move from D to C is same. Alright? That is for the second Kepler's law. Okay, next we will go to the third Kepler's law. Okay. So third Kepler's law is actually obey this law. The time taken for the planet to orbiting the sun will be proportional to the cube of the radius of the semi-major axis. Alright, so you already have the formula that, okay, why we use the centripetal force, the formula of centripetal force, because that the planet will always orbiting the sun, in which the sun will be at the focus, okay, at the center of the focus. So that's why we will use the centripetal acceleration force. So the centripetal acceleration force will be equate to this one. The mass of planet times with the velocity squared over r will be equal to the gravitational force here. Okay, the gravitational universal force. Okay, so up to here you can eliminate dm. Okay, you can eliminate the mass of the planet. Okay, so you will left with v squared over r equals to g mass of the sun over r squared. Okay, so right now you can eliminate the r. Okay, then you will left with v squared equals to gm sun, okay, over r. Alright, up to here, v, okay, we know that our v comes from distance over or displacement over time. So your displacement right now is 2 pi r. Okay, as your circumference right now is 2 pi r over t. Then this one is squared, so you have to do the squared here, equals to g m sin over r. Okay, right now our main concern is to make sure that the t squared equals to proportional to the radius cube. Okay, so right now what you have to do is you have to make t as the subject. Okay, you have to make t as the subject. Alright, so right now you will have 4 pi squared over r squared over t equals to g ms over r. So right now we want to make sure that t will be the subject, so I will write it here. So 4 pi r cube, okay, I move the r upward, okay, over g ms equals to d t squared. Okay, so right now we want to factorize the r, so t squared will be equals to 4 pi g ms over r cube. So 2 squared will be equal to the proportional to the r cube. So here we have another constant in which this constant will be denoted as Ks. Okay, you can take a look on your textbook if I'm not mistaken, page 216. Okay, so basically for this value we want to find the mass of the sun. Okay, the question will ask you to find the mass of the sun. Okay, so right now take a look on the example 7.13. From a telecommunication point of view, it's advantageous for a satellite to remain at the same location relative to a location on Earth. This can occur only if the satellite's orbital period is the same as the Earth's period of rotation, approximately 24.0 hours. At what distance from the center of the Earth can the geosynchronous orbit be found? B. What is the orbital speed of the satellite? Okay, so for question number 1, it asks you to find the distance from the center of the Earth. Okay, and it already give you the time taken here, okay, for the satellite to orbiting the sun, which is 24 hours. So this 24 hours, you have to convert into second. Means that 24 times with 60 minutes times with 60 seconds, then you will get 86400 second. Okay, and then you can substitute in your formula here, and then for pi, okay, just write the pi squared, and then G is your gravitational universal constant, which is 6.67 times 10 to the power of negative 11, and then times with the mass of the Earth. Then you can calculate your radius 3. Okay, don't forget to cube root. Then you will get 4.22 times 10 to the power of 7 meter. Okay, for this one, you just substitute all the information given. Okay, and then for B, how you want to find the speed? We will use the equation, okay, on the chapter 2, in the chapter 2, which is velocity equals to displacement over time. Your time right now is 24 hours, then you have to convert into second. Then your displacement here is 2 pi r. Why? Because the satellite will be orbiting the Earth in circular motion. So that's why we will use 2 pi r. So substitute your r, okay, your r from here, substitute your r from here, and then you will get your velocity. So I think we are finished with chapter 7. Then I hope you can do the tutorial. I will give you the question for the tutorial and submit to me on Friday. Thank you.